All right, so we're going to go ahead and get started. Welcome to this session. This is the Prebiotic Chemistry and Early Earth Environment session on the origins, inventories, and geologic settings of the building blocks of life. We're your session chairs. I'm Lori Barge from NASA JPL, and this is Danielle Simkus from NASA Goddard. And so then introducing our first speaker, Tomislav Solar.
Thank you very much. I hope you all hear and see my presentation. So this is my AbSciCon talk. Welcome to this presentation titled "The Effects of Geological and Environmental Conditions on the Rise of Prebiotic Peptides on Mineral Surfaces." I'm Tomislav Stolar, a PhD candidate. I work at Ruđer Bošković Institute in Croatia. Here are my contact details, and I thank all co-authors with whom I worked on this project. The importance of prebiotic peptides in a prebiotic world is obvious. It is hypothesized that they were included in a molecular symbiosis with nucleic acids, and they have really important catalytic properties. There are different literature approaches on how to synthesize oligopeptides, and they mostly, understandably so, rely on reactions in aqueous solutions. However, from a thermodynamic standpoint, condensation of free amino acids in aqueous solution is thermodynamically unfavorable process. And here I would refer to Everett Schock's talk at AbSciCon, when he said that when seeking a biotic organic synthesis, we should stop fighting thermodynamics. If we do that, if we stop fighting thermodynamics, we would have to move away from aqueous solutions, and we would end up in dry environments. So the availability of dry land on prebiotic Earth is often discussed, but it is considered that there was some land available on the emerging continents and near volcanoes. If you want to do organic synthesis in the solid state, probably one of the best options would be to use mechanochemistry. Mechanochemistry is a very vibrant research field that is compliant with the principles of green chemistry. It uses mechanical activation to induce chemical reactivity in the absence of solvents. And there are different types of mechanochemical instruments which exert different mechanical forces on the reaction mixtures. There are vibratory ball mills, planetary ball mills, and extruders. And when talking about mechanical energy on the prebiotic Earth and in the context of origin of life, it is mostly associated with surface impact events. However, the relevance for prebiotic chemistry is hard to predict, given the uncertainty and frequency of their appearance over time. But the sources of mechanical energy on early Earth could have been much more diverse. For example, they could have included tectonics, earthquakes, but also geomorphological processes such as erosion and weathering. Specifically, erosion and weathering are known to occur more frequently and are capable of exchanging matter on the planetary surface. The use of mechanochemistry in prebiotic chemistry has been demonstrated in the literature in the cases of amino acid derivatives and sugars. So in our work, we try to obtain oligopeptides by mechanochemistry, and we explore different reaction parameters, namely the effects of temperature, mechanical loading, time, atmosphere, real mineral surfaces, and different combinations of amino acids. So when considering the effect of temperature, we milled glycine with titanium dioxide in a ball mill. We used this kind of setup that was developed in our lab, which enables us to perform temperature-controlled mechanochemical reactions. Some of these findings have already been published last year. And by ion pairing high-performance liquid chromatography, we could see that by increasing the milling temperature, we obtained longer glycine oligomers, alongside with the formation of predominant part of the reaction mixture, which was cyclic diketopiperazine. So total yield of linear oligomers was the highest, around 10%, when the reaction was performed at 100 degrees Celsius, where we obtained Gli8 oligomer. Also, we validated some of the results by LCMS, quadruple time of flight analysis. Here we see the results for the reaction where glycine was milled with titanium dioxide at 130 degrees Celsius, where we observed oligomers up to Gli11. Next, we turn to different amino acids. So this is a chromatogram for milling glycine with alanine with titanium dioxide at 100 degrees Celsius. We can see that there are several peaks, which would indicate that there was some reactivity. And by direct injection to MS, we could confirm that glycine and alanine dipeptides, as well as tripeptides, have been synthesized in this way, thus demonstrating that other amino acids can be incorporated into a growing peptide chain. After that, we explored the different amounts of mechanical loading that is transferred to the reaction mixture. We could do that simply by variation of the milling frequency. So for example, when the reaction of milling glycine with silicon dioxide at room temperature for 96 hours was performed at 5 Hertz, we could detect the presence of glycine tripeptide. So milling frequency of 5 Hertz is a very low frequency, which could mimic, for example, erosion or weathering processes. So also we did milling of glycine with titanium dioxide using 3 hand-picked stones as milling media for 18 hours at 20 Hertz and ambient temperature. Results from IPHPLC show that glycine oligomers up to tetrapeptide have been formed in this way. After that, we explored the effects of time. So as hypothesized, it was demonstrated that time is an important parameter. So when comparing reactions that were performed from 1 hour up to 96 hours or 4 days, we could see that there is almost exponential increase in the total yield of linear oligomers, around 2.5% when the reaction was performed at 40 degrees Celsius and for 96 hours. We also explored the effects of different atmospheres. So here we used nitrogen and carbon dioxide as one of the 2 primary components of early Earth atmosphere, and by LCMS triple quadruple, we could show that the glycine oligomers up to Gli7 were formed when milling in nitrogen atmosphere, and glycine oligomers up to Gli6 were formed when milling was performed in carbon dioxide atmosphere. Finally, we turned to milling with real mineral surfaces. We managed to obtain 10 different classes of minerals representing different mineral classes. And by LCMS triple quadruple analysis, we could detect that one of the best minerals for producing oligopeptides were calcite and magnesite, where we formed glycine tetrapeptides. But the best was quartz, so crystalline silica, where we detected glycine heptapeptide. For example, here are the chromatograms of LCMS triple quadruple analysis using magnesite, where Gli4 is observed, and quartz, where oligopeptides up to glycine 7 residues have been formed. Finally, at the end, we were interested to see if the oligomerization under mechanochemical conditions also proceeds if amino acids are reacted with hydroxy acids to form deoxypeptides. Therefore, we mill glycine and glycolic acid, and we could observe by MALDI time-of-flight analysis that dimer, peptide dimer, was formed in this way alongside at least 4 other peptides. And the longest peptide obtained in this way, so by milling glycine and glycolic acid with silicon dioxide at room temperature for 16 hours and at 30 Hertz, we obtained oligo peptide containing 3 glycine residues as well as 3 glycolic acid residues. So in summary, the formation of peptides is operational under different geological and environmental scenarios in a dry prebiotic setting. This might have implications for astrobiology research and reconsideration of extraterrestrial conditions that can give rise to peptides. For example, a weathering of amino acids in dry settings on mineral surfaces might result in peptides. With this, I want to end and thank all of my co-authors and the funding agency, and I thank you for your attention, and I'm now open for taking questions.
We have time for a couple questions.
Thanks for an interesting talk, John Yen, University of Wisconsin. In your characterization of peptides on minerals, I wonder, did you do this on a mass basis of mineral, or do you have some way of quantifying the surface area? I think the minerals you showed have a number of different, probably surface areas per volume. Could you comment on that?
Thank you very much for your question. I will just share this screen again. So what we did was we used an excess of mineral surface with respect to the glycine amino acids. You know, we wanted to respect that there was, more available inorganic material when compared to organic material, for example, on early Earth. Therefore, we used 5:1 molar ratio in favor of excess of minerals. So this is the variable that we used. So far, we still didn't check the surface areas, but this is still an ongoing study, so we will have more data on this, I hope.
Thank you.
Hey, really amazing talk. I'm Luke Stella from the Australian Centre for Astrobiology. I was really interested with the time experiments you did and curious why you stopped at 96 hours when it seemed to be getting really good. Like, could you run it for months, or I don't know, like what's the end limit there?
Thank you very much, Luke. Funny that you asked this question. Because my research group is predominantly in the mechanochemistry, let's say, research area. I'm the only one working in the prebiotic chemistry or origin of life. Therefore, we have several milling instruments and a big research group. So the time that is available to perform the experiment is limited. And believe me, I pushed as far as I could. I almost got expelled from my research group. Just joking, of course, but this is the only reason basically why we stopped at 96 hours. We could, of course, do longer milling, but this also puts a lot of stress on the milling instrument, which, of course, is prone to breaking. So yes, thank you. Maybe we will try to also do one experiment at least with longer milling time.
Just like leave it over the summer holidays or something and come back in 3 months and yeah. No, thank you. That's great.
Thank you very much.
One more question? Do we have time or no? Time for one more. Okay.
Hi, I'm Ellie from CU Boulder, and I saw that you had 3 different minerals that you were saying were really good at this. Is there anything universal about the surface chemistries between these 3 minerals that are kind of good at promoting this kind of reaction? Like, what is it about the surface chemistries that's leading to this? And can we use that to predict what other minerals would be good at this?
Thank you very much for your question. As I said, this is still an ongoing part of the project. Maybe I could give the best answer for quartz mineral, since most of our reactions We used silicon dioxide, you know, the same commercial one that people use to fill the columns. So it's not surprising that quartz, which is a crystalline silicon dioxide, would have like similar reactivity and ability to produce oligopeptides. We didn't go into mechanistic studies, but what I can tell you from the literature is that titanium dioxide as well as silicon dioxide, there have been some computational studies, you know, showing that they have adsorption properties as well as properties of binding water molecules that are released during the reaction when oligopeptides are formed. So there is this kind of dual role. But of course, these studies are on very, let's say, simple minerals, as I said, titanium dioxide or silicon dioxide. So at this moment, I could not give you a better answer. But this is certainly very interesting.
Thank you very much. All right, we're going to move on to our next speaker. Our next speaker is Kelvin Smith.
Okay, thank you very much. My name is Kelvin Smith. I'm a 6-year PhD student, a PhD candidate from Georgia Tech, and I want to thank AbSciCon for having me speak today. So my presentation is on thermodynamic and kinetic investigation of oligomerization and degradation of peptides under prebiotic earth conditions. Let's get started. So to introduce the topic, I want to say why this research is important. The origins of life is a long-lasting puzzle that has been trying to be deciphered for many years. One of the major hurdles of it is through peptide bond formation because of the formation of diketopiprazine and the thermodynamic unfavorability of that sort of reaction. So how is that able to be formed under plausibly prebiotic conditions? And one molecule is a simple molecule, but it's of paramount importance, so much so that it's studied in the literature quite a bit, in lactic acid and how it can form polyesters, which could be the first step into forming a peptide. So these are protopeptides. So what do we know and what we don't know? So what we know is in the kinetics of lactic acid, we are aware of certain mechanisms such as backbiting and scission. So backbiting forms a 6-membered ring on an OH terminus of a dipeptide to form a cyclic ester or cyclic amide. And scission can cleave off a certain ester moiety on any sort of peptide, on any sort of diester. And we also know, thanks to from Dr. J. Forsyth about ester-amide exchange, that there's a plausible pathway towards peptides. But what we don't know is what are the thermodynamic driving forces that go towards exchange and this oligomerization or esterification of lactic acid or similar hydroxy acids, and are we able to quantify them? So that's what our experiment or our research is about. I make a chemical model that would help create energy plots, Gibbs energy plots as a function of pH and pKa of monomers and dimers. And the contour map, and I also make contour maps that display conversions towards products. And the hypothesis, so we hypothesize, is pH and pKa do play a major role in the thermodynamic driving forces, mainly the pKa shift between monomers and dimers. But the temperature, because of the thermoneutrality from Witzke and Vu for simple oligomerization of esters, kind of plays a little bit of a minor role. So my methods is I first start with a working reaction, a very simple overall reaction of esterification. values, and I break it down into dissociation states. And each of those dissociation states are a function of pH. The amount is dependent on pH. And that amount is further dictated through stoichiometric coefficients, which are the mole fractions of these association states. Then I will perform an atom balance. So I deal with carbon, nitrogen, oxygen, hydrogen, broken down reactions. And depending on the pH, the hydrogen balance especially may not be satisfied as written. So then I would then need to add appropriate number of hydrogens as needed to the reaction while still making sure that the reaction is satisfied. Let's see, next is the thermodynamic calculation. So all of the Gibbs and energies and enthalpies of formation were acquired using density functional theory, or DFT. The conversions were the equations for the conversions were either derived, or for the case of esterification, there was a closed system equation provided in the literature by Hershey that would allow us to compute these conversions. And then I make a Van Hoff plot where I compute equilibrium constants for different temperatures, provided that the enthalpy of reaction is constant across temperature range. So here's a list of all the important alpha hydroxy acids. These are also molecules you see from groundbreaking experiments such as the Miller-Urey experiment in the 1950s. You see the glycolic acid and lactic acid and their anionic forms, and also in their dimeric forms. So I want to go through, step by step to see where the process on how I conducted the research. So we start with the working reaction. We have 2 lactic acid residues going to a dimer and water. Now the reaction, as you see there, is not going to occur all the time. For instance, at pH 7, the lactic acid monomer and the dimer is going to be in their anionic state. So we would have to break that reaction down further into this reaction you see down here, where you see X1 and X2 are the mole fractions of each of these association states, A and AA. And also I use alpha, beta, and gamma. I even broke down water into their dissociation states. And using that broken down reaction, I then do atom balances to be able to figure out what relationship exists between the stoichiometric coefficients and pH and pKa, which is what this next slide is going to be talking about. So the stoichiometric coefficients that you saw are tied to the pKa of each species. And I calculate them using this ratio you see here of a Henderson-Hasselbalch type of equation. We have pH of solution is equal to pKa of the species plus the logarithm of the conjugate base in the acid. And that ratio in the logarithmic term dictates what the coefficients are. And the mole fraction of each of those association states from that ratio can be found using this expression, mole fraction of dissociation state J of a particular species M can be found using that. So by combining those 2 equations, we get the result that the mole fraction is of each species in solution at a particular pH. At a particular pH is actually a function of both the pH itself and also the pKa. Now, some of the pKa's were experimentally undetermined. So for instance, the lactoyl lactic acid hasn't been determined, its pKa hasn't been experimentally determined. So instead I use benchmarks of a compound that I've used before. Of a compound that has been used, like O-acetyl-lactic acid, which had a pK of 2.74. Or I do a small grid search to vary them as I conduct, as I make my model in MATLAB. Here's the expanded delta G of reaction, where we have, it's just a classical products minus reactants. And we see the mole fractions. You can consider the mole fractions of each species as a weight of on the delta G of formation of these of all these species, which are found from DFT. And because delta H is a state function, we can use the exact same formulation, except instead of delta G's, we use delta H's. So if we combine that, we get a graph that looks like this. So here we see the delta G of formation as a function of pH for the oligomerization of lactic acid, just for monomer to dimer. And we can see that pKa does play a major factor here. And we can see that around pH of 3.7, 3.8, if the pKa is around 3, we can see that it's at its most spontaneous at around that point. But there are other places where delta G is very highly unfavorable. But there are certain pH ranges where this reaction is naturally spontaneous. And here's a Van Hoff plot. And we can see here that the temperatures that the profiles of the delta G are very tightly packed. This suggests that the thermal neutrality does hold. Temperature does play a small role, but not as major a role as the pKa's. And then here we talk about the conversions. So the color contours are the conversions of lactic acid. And these conversions were computed using this equation you see to your left from Hershey, where we use the equilibrium constant, the initial water content, W0, and then lambda 10, which Hershey describes as the first moment of monomer. So basically it's just saying how much initial monomer do we have in solution. And this red line you see here is from an author named Holton, who has done pH and thermal work on polylactic acid acidification at room temperature, but he didn't report conversion data. But I just plotted, but he did have pH and W0, so I was able to plot that. And we can see here that as we dry down, while holding pH constant, we can see that conversions do increase as we would expect. But we can see that we can also increase pH at the same water content by decreasing pH, by increasing the yield of longer oligomers of lactic acid. So conclusion, we can see that the polycondensation thermodynamics is driven by both pKa and the removal of water from the system. Polycondensation could proceed from both neutron and anionic states thanks to the atom balances and the pH and pKa considerations. And even though I didn't mention, and even though I didn't say it in presentation, but chirality, whether the diastereomers do play a minor role in thermodynamic driving forces, and dissociation states were critical in understanding the ester bond linkage thermo. And future steps, I was going to work on the second part of the coin, which is about depsipeptide exchange, swapping an ester for an amide bond, and I'm doing work with a similar thermodynamic analysis for that reaction. So I just want to say thank you very much. I want to thank my advisors, Dr. Martha Grover and Dr. Charles Leota for supporting me, and Dr. Moran Franco-Penner and Dr. Jay Forsyth for supporting me throughout my journey through my PhD. And my email, you can see ksmith427@gatech.edu if you want to contact me for more questions. Thank you very much.
Time for a question.
Thanks for the nice talk. Do you also account for reverse reactions where you hydrolyze the products?
I'm sorry, can you, I couldn't hear you, I'm sorry.
Yes, I was just wondering if you consider the hydrolysis of your products, if you consider the reverse reactions, or are they fine to neglect?
Oh, are they fine to neglect the reverse? Well, I did include reversibility in my model. I did take into consideration the equilibrium constant of products over reactants, but in terms of whether it mattered a lot, I'm not entirely sure about that. I'll have to get I can get back to you on that if you need more detail on that, but I'm not entirely sure. I can't. I'm I don't know if I'm processing that right. Oh
Okay,
my
thanks.
goodness. I'm sorry.
Any other questions?
I'm sorry.
If not, then let's thank our speaker.
So,
So our next talk is withdrawn, and so in order to stay on time for the future talks, we'll start with our next speaker at 3:45. So we'll take a short break until 3:45. Nice. Starting when? I guess whenever I'm ready. Maybe next year, maybe early next year. Oh, cool. Okay. Let me check. All right, we're going to get started again with our next speaker, Laura Rodriguez.
Hi, everyone. My name is Laura Rodriguez, and I am a JPL postdoc. And today I'm going to be talking about my research, which is focused on studying conditions that are conducive for phosphorylating or adding a phosphate group onto organics and aqueous solutions. So phosphorus is really important for life, all life on Earth today, and it's thought to have been critical for the origins of life on the early Earth. However, in its most common form as phosphate, it would have been difficult to accumulate in the oceans, and that's because, as shown in this diagram here, okay, my mouse shows, under a wide range of pH from acidic solutions to alkaline conditions, you have to contend with common cations chelating the phosphate and precipitating out as insoluble minerals. In addition to that, phosphorylating is thermodynamically not favorable under aqueous conditions, and that's because it's a condensation reaction, which means that it produces water as one of the products. And when you are in water, you're essentially surrounded by one of the products, and so equilibrium is pushed towards back towards the reactants. There are mechanisms to get around that issue if you do the reaction in non-aqueous solvents or semi-hydrous solvents. But for the purposes of this work, I was interested in focusing on aqueous conditions, and that's because this is more representative of the kind of solutions you would encounter in the deep sea or on the early Earth, as well as the oceans of other worlds such as Enceladus and Europa. So a potential workaround instead is phosphite, which is a reduced form of phosphorus. It's HPO3, and you can actually get phosphite from phosphate by reducing heating with ferrous minerals or through lightning strikes. And phosphite, unlike phosphate, is actually much more soluble in the water, so you can overcome that solubility problem. In addition, Pasek and colleagues in 2008 showed a way to get around the thermodynamic problem by coupling phosphide oxidation with Fenton chemistry to produce phosphorylating compounds. So Fenton chemistry is just the oxidation of ferrous iron, shown in the first line here, with a strong oxidant like hydrogen peroxide. And you can produce ferric iron as well as a hydroxyl radical. And the hydroxyl radical can then go on to react with the phosphite, producing a phosphite radical. And then you can form phosphate, and then you can have phosphite and phosphate radicals combined to form pyrophosphate, triphosphate, and trimetaphosphate. And these are all phosphorylating agents, which means they readily give up their phosphate groups onto organic compounds. And so now we have actually a new problem, which is this reaction actually generates hydroxyl radicals that can react with organics and actually destroy any organic you want to phosphorylate in the water. And so that comes to my research, where I am interested in looking at condition spaces where you can generate a lot of these polyphosphates while minimizing organic degradation. And typically these reactions are done with dissolved iron at around pH 4. And so I was interested in doing the reactions with manganese, and that's because manganese is an antioxidant, as well as at higher pHs. And that's because not only are those higher pHs more relevant for Earth's early oceans, but also because at higher pH, iron and manganese crash out to form oxyhydroxide minerals, which themselves could potentially provide an avenue for preserving the organic compounds. So for this work, I generated my own minerals using ferrous chloride or manganese chloride and titrating with sodium hydroxide to either pH 5, 6.5, or 8. And then I added a solution of phosphite glycerol, also titrated to the corresponding pH, and then oxidized it last with hydrogen peroxide at 500 millimolar. All of these reactions were done under anaerobic conditions, and the results were the reactions were analyzed using nuclear magnetic resonance spectroscopy, or NMR. So shown here is 31 phosphorus NMR. So each of these peaks corresponds to a phosphorus species. So PA is phosphonoacetic acid. That's a standard we spiked in. HPO3 is our starting phosphite, and you can see there are two products, phosphate and pyrophosphate. And so this goes to show this reaction was done at pH 8 at room temperature. And so at this pH, iron is mostly present in the mineral oxyhydroxide. And so this is just showing that the mineral is capable of facilitating this reaction. We also looked at it at higher temperatures, so in this case 70°C, because we wanted to see if that could really facilitate the formation of pyrophosphate. But what we found is that it didn't actually increase the yield of, where's the mouse? The yield of phosphite oxidation, and instead decreased the amount of pyrophosphate present, and that's because pyrophosphate's actually unstable under high temperature, so it was just hydrolyzing back to phosphate. So moving forward, we decided to do our reactions at room temperature. What this diagram is showing is a comparison over time of the amount of phosphite that's oxidized over the course of a month when we did the reactions at pH 5, 6.5, or 8. So you can see here that within 24 hours, the reaction's essentially complete under all conditions. And in general, the reaction yields are pretty high, so between 75 to like 95%. Dissolved iron was promoted the reaction more than when the iron is trapped in the mineral. But overall, we had good yields even with the mineral. And in general, pyrophosphate formation was between 10 to 18%. So then we decided to look to see what was happening to our organic in solution. In this case, we used glycerol, and that's because if you can phosphorylate glycerol, that's an important component for phospholipids. And what this top graph is showing here, top plot, is Proton Nmr. So we have our phosphonoacetic acid, our glycerol, and our starting phosphite. And this is just showing that with the mineral, the glycerol is stable. But as soon as we add peroxide and get the Fenton chemistry going, it degrades and forms all of these different peaks. This large peak here actually corresponds to formate. And so what this is showing is that even with the mineral, we get glycerol oxidation. So it isn't able to prevent oxidation of the organic compound. What the diagram I'm showing over here is, I was just showing that there's been a lot of work looking at glycerol oxidation with hydroxyl radicals. So here are just some of the products you would expect to find. So even though it can't prevent glycerol oxidation, I wanted to see how it compared to how much glycerol was oxidized under the other conditions. So that is what this plot is showing here, the percentage of glycerol oxidation over time over the course of a month. What you can see is, as expected, at pH 5, more glycerol is oxidized compared to pH 6.5 and 8. So that's not surprising considering that more phosphite was also oxidized under these conditions. And in fact, it's about a 1-to-1 ratio. Intriguingly, though, at pH 6.5, we actually have proportionally more glycerol being oxidized than we did have phosphite being oxidized. And so it was actually a little bit more than a 1-to-1 ratio. And then the opposite is true for pH 8, where we had if you recall, about 75% of the phosphite was being oxidized, and the significantly less glycerol is oxidized, so it's a less than 1-to-1 ratio. So although glycerol is still oxidized under these conditions, the oxidation is somewhat inhibited at pH 8. So then if we switch gears to manganese, all three of these spectra are phosphorus Nmr of the manganese reactions at pH 5, pH 6.5, and pH 8 over the course of a month. And what you can see here is a phosphate peak is present in all of them. So that's just showing that manganese can facilitate this kind of chemistry under all of the conditions. So whether dissolved or whether present as an oxyhydroxide mineral. We only actually observed pyrophosphate, you can see this trace peak here, when it was present as a dissolved metal. In fact, the reaction is just very, very slow, even at pH 5, but it's especially slow when it is trapped as an oxyhydroxide mineral, as you can see by the overall yield shown here. Looking at the Proton Nmr spectra to see how glycerol behaved, we found, so the top spectra is the reaction with manganese at pH 5 after 24 hours. So we had about 8% phosphite oxidized at that time point. And the bottom is at pH 6.5 after the course of a month, so about half of the amount of phosphite was oxidized at this point. And what you can see here on the top part is that when manganese is dissolved, the glycerol still oxidizes, so we see a really large formate peak here. So it didn't prevent oxidation. But when it's present as an oxyhydroxide mineral, we did not observe any oxidation of the glycerol. And that was surprising because even though it was relatively low yields of phosphite that was oxidized, you would still expect to see at least a small trace peak of the formate. But we did not see anything. So that seems to suggest that maybe this is an avenue for generating polyphosphates while minimizing organic degradation. And in fact, previous work has found that when looking at the Fenton chemistry facilitated by manganese, either dissolved or at pH greater than 6 where it is precipitated out, it proceeds through two different mechanisms. So when it's dissolved, it's like iron, it produces hydroxyl radicals. But at pH greater than 6, it produces reducing radicals that actually react with organics differently. In this case, perhaps those reducing radicals are not reacting with the glycerol. So while this is a promising avenue, these reactions are very, very slow. And so we would ideally like to run them for much longer than a month to actually see if this trend holds true when more phosphite is actually oxidized. But that did lead us to question whether mixed iron manganese minerals could be a good avenue for maximizing this kind of reaction. So what this is showing is a range of iron and manganese at different ratios. And as predicted, you can see that at 100% iron, we had the most oxidized and that it decreases with iron. And then when looking at the amount of organic that's oxidized, you can see at 100% iron that a lot of the glycerol was oxidized as predicted. And we do see that trace formate peak in other reactions. But what really intrigued me is that the glycerol peak just disappeared altogether when we had mixed iron manganese minerals, which was strange. I'm not quite sure what happened to the glycerol. We did have controls, so we did run it without the peroxide, and the glycerol was stable. So I don't think it's absorbing to the mineral unless it only absorbs to the oxidized mineral, but that would be surprising given the structure of glycerol. And if we zoom here on the formate peak, you do see that trace formate peak in the reactions, and so it's actually a lot less than you would expect considering how much phosphite was oxidized. So no matter what, the oxidation of glycerol seems to be inhibited, but where it went remains uncertain. And so these are the overall conclusions, and I would like to thank my advisor, Dr. Lori Barge, as well as my other co-authors, Dr. David Vandervelde and Dr. Matthew Pasek, and thank you all for your time and attention.
Time for a couple of questions.
Hi, Laura. Matt Pasek, USF. So I'm curious where your glycerol went then. I mean, do you have any, I guess you have some amount of speculation, but anything specific? Or?
About the glycerol?
Yeah.
Yeah, so I was thinking that perhaps that since it is a different radical that forms with the manganese when it's crashed out as a precipitate, that different radical is reacting with the glycerol. And the reason that you don't see that with just manganese is perhaps having that iron there really promotes that reaction as well. But at this point, it's kind of speculation. I just find it, I just wouldn't expect it to actually absorb to the oxyhydroxide mineral. That doesn't seem likely, but we will test that just to make sure.
While we're at it, do you have, I'm here. Do you happen to know what the oxidation states that were sampled by the manganese? I mean, you were introducing at manganese 3, I'm assuming. Did you see manganese 4? I'm assuming you never saw manganese 7, but did you?
Oh, no, we didn't investigate the oxidation state of manganese. I just know that it started at manganese 2. We are getting a cation IC, though, so that is one of the things that I'm interested in looking at.
But it didn't turn purple.
It didn't turn purple, it turned brown.
Any other questions? If not, we have time, so I'll ask a question. So what do you think would be the effect of if your iron was in varying redox states, such as if it wasn't just an Fe2 hydroxide, but a mixed Fe2, Fe3 hydroxide?
Ooh, good question. I believe Matt has actually done some work on that, and the reaction still proceeded with ferric iron, right? In fact, I think it was actually more efficient with the ferric iron, or I forget what the actual result was, but that is a good question. I'm not quite sure.
Thank you. All right. Thanks very much. Our next speaker is Matt Pasek.
Hello, everyone. Thank you kindly for the invitation to speak. And today, I should note as well that this is actually, Maheen Gull should be the lead author on this paper, but instead has two small kids and asked me to present in her stead. So it is a continuation, similarly, of what Laura just presented on Fenton chemistry and reduced phosphorus and the potential of doing something interesting with that. And I'll show you some of the results here. And so her title here is An Early Earth Predisposed to Phosphonylation and Phosphorylation by Reduced Oxidation State Phosphorus Compounds. So phosphorylation is the addition of phosphate. Phosphonylation is the addition of phosphite. Sorry for the names. The phosphorus people got a hold of things and added many years ago, and it becomes very hectic, especially when you start talking about all the various forms of phosphorus, including things like hypophosphite, which is shown here as 1, and phosphite, which is 2, and there's a hypophosphate, which is a +4 oxidation state, and there's phosphate, which is shown here, and then pyrophosphate, and there's a pyrophosphite. It gets confusing quick. What we have been looking at is the potential of reduced forms of phosphorus being able to oxidize and form reactive phosphate compounds that could then perform key reactions. And Maheen specifically was investigating the reactions between reduced oxidation state phosphorus compound hypophosphite, and that's what we'll show specifically here. So instead of phosphite, it is a 1+ oxidation state that can then react with the oxide generated by the Fenton chemistry and produce reactive phosphorus compounds. We specifically investigated the reactions of uridine and adenosine in this experiment as well. So the generation of reduced oxidation state phosphorus compounds, Laura showed kind of the general scheme of it right here. It's a radical-induced reaction. The Fenton chemistry specifically forms hydroxyl radicals when using iron 2, and those hydroxyl radicals rip up that hydrogen-phosphorus bond and slowly start to oxidize it. And the interesting thing is you can get a sort of possibly a reactive intermediate that can form the pyrophosphate, triphosphate, and the cyclic triphosphate as sort of the oxidized final products. It's roughly a 70 to 20 to maybe 3, I guess my math's not adding up right there, 70 to 25 to 3 to 2 ratio of those 4 types of compounds here. And so originally you use some reduced forms of phosphorus, oxidize those, and you can create condensed forms of phosphorus, condensed phosphates that have been used previously in several reactions to promote phosphorylation reactions. So the question, of course, then you might have is where are these things coming from? Reduced phosphorus, you can ask, there's roots from diagenesis, where you take iron 2 and react with phosphate at 200 degrees Celsius, and you can make phosphite. You can do lightning, you can have meteoritic materials corrode, and they will release some phosphite too. There are some other sources that are that we're working on even now that it may have been an important constituent on a prebiotic Earth. Peroxide is a pretty strong oxidant, but it is also formed through UV photolysis of water. It's found as sort of an ice photolysis or radiolysis product, for instance, on Europa. So there are ways of making a pretty strong oxidant and a pretty strong reducing form of phosphorus. Now, the interesting thing is that reduced phosphorus is actually pretty stable. We have left a vial of phosphite in water stored under air, sit for 5 years, and had 0.1% oxidation. So this is not a unstable compound that is something that you would need to worry about oxidation from air or other compound or other oxidants in the environment. Most of what we do is phosphorus 31 Nmr, which is the ppm scale down here. And so this is starting material. This is hypophosphite. And it is a triplet because there's 2 hydrogens bound to the phosphorus. And then when you add the iron and peroxide to that, you will form the phosphite in addition to phosphate here. And a phosphite's peak B, phosphate is a peak C here. And there are the pyrophosphate and triphosphate that are formed at lower concentrations further upfield here as well. So what Maheen did specifically was take a nucleoside, in this case uridine, and then after, so I should note after, the
the 24 hours that this reaction was subjected to the Fenton conditions and it kind of finished, she added uridine as well as a couple other compounds such as urea or ammonium hydroxide, and then took a look and see what you have. And so again, going from the more, the sort of oxidized products of this prior sort of inorganic spectrum right here, and then adding after the fact a nucleoside, you see there's a lot of new compounds that have come about. And these compounds are a number of different styles of organics, mostly organophosphonates, but also a fair bit of organophosphates. And so these include 2', 3', 5' phosphites of uridine, as well as the phosphates. There appears to be some dimer, and I'll show you some of that in a little bit. And we do have some cyclic diester as well. The total amount of organic phosphorus that she is reporting from the integration of the NMR shown here is on the order of 22 to 76%. And that is as a fraction of phosphorus that is visible within the phosphorus NMR. So sort of a larger perspective of this in a sort of more whole field, we as well use phosphonylacetic acid as our standard, which pops up at our pH at about about 15.5 ppm. And then over at the sort of 20 ppm is the cyclic phosphate, the 2', 3' uridine phosphate. And then you see that the inorganic phosphorus compounds, as well as the organic phosphates and organic organophosphonates, are present at these lower ranges right here. And then blown up right around -1 is what we believe to be diesters. So that is uridine phosphate uridine. And there is a sort of chemistry that's going on with this. This is they add this stuff to the compound and then let it sit and slowly dry out. I should add that she is doing this at around 58 to 65 degrees Celsius. And then to see what sorts of phosphorylated organics she is producing. And again, you have some of the uridine, we spike this with authentic sample of uridine 5' monophosphate, and indeed the peak E here is one that rises when spiked here. So to summarize what she sees with uridine, we have our uridine starting product, and then we have the uridine phosphates from the 5', the 2', the 3', and then the cyclic 2', 3'. In addition, there are the phosphites, also probably in a similar condition, but you do not form the cyclic uridine phosphite because there is no negative charge on the phosphite to kind of keep it stabilized. And then as well, there are the dimers that are being produced there. And then if you take adenosine, you see something very similar. The adenosine also forms adenosine monophosphates and adenosine monophosphites, as well as the adenosine cyclic 2', 3' phosphate. There is also this peak corresponding to a dimer as well. I should add that when sampled by mass spectrometry, these peaks were all matched to a specific M over Z, so there is mass spec evidence for each of these compounds as well. So again, very similar compounds that are formed with using adenosine in place of uridine, suggesting that this style chemistry could work, again, after the fact, as opposed to being subjected to the oxidizing conditions of the Fenton chemistry. And then using deoxyriboadenosine and subjecting that to these conditions, we took a look to see if the similar chemistry would come about. And intriguingly, you see here that there is no peak corresponding to the dimer in this case. The dimer would appear between 0 and -2 right here, and it's not there. And there is additionally no cyclic 2', 3', because it is not possible with the deoxyadenosine, and suggesting perhaps that the cyclic uridine or adenosine 2', 3' is the key intermediate forming the dimer here. So the late addition of the organics to the solution, so after the Fenton chemistry has kind of burned off much of the oxidant, appears to be necessary. And Laura showed that very well, that glycerol is getting ripped up by the Fenton conditions pretty clearly. We took a look to see the stability of adenosine. So if you take adenosine, this is a carbon-13 NMR, sort of the standard adenosine, and then subjected to 1 day of reaction in Fenton chemistry, you see some of these peaks are starting to drop down. 2 days, and then 3 days right here, effectively all the carbon has become carbonate or similar fully oxidized forms of carbon. So the addition of organics, it unfortunately is not a one-pot reaction that we often seek in prebiotic chemistry, but is at least a two-pot reaction in this case. Problematic, but there is some promise as far as forming dimers and other compounds in this chemistry here. So to kind of summarize, the best reactions between 70 and 80% yield of total organic phosphorus, that includes the organophosphonates as well as the organic phosphates. It occurs when you use urea and ammonium as constituents of this chemistry. She's done this experiment now several dozen times and has been able to get these results at least reproducibly. And her chemistry suggests that the ammonia compounds, including ammonia from urea, seems to be kind of very helpful in generating reactive phosphorus compounds that promote condensed phosphates that we are looking for in sort of our prebiotic chemistry. And the dimers seem to be coming out in this chemistry as well, and organics could potentially survive some of the harsh peroxide conditions. They're gone in about 3 days, but one day there is still some adenosine left as well. So with that, I'll say thanks to our collaborators and our funding agencies and take any questions.
We have time for a couple questions.
Great talk. So I have a question. How much peroxide do you need to have those reactions? Is this prebiotically plausible scenario?
Right. That is a good question. So you need a fair bit more stoichiometric peroxide than iron. So roughly you need 4 equivalents of peroxide to every hypophosphite or 2 equivalents for every phosphite. That's a fair bit. It is added. You can add it slowly over the course of a day, or you can add it all at once. There is not really a lot of difference in the chemistry, the final resulting chemistry, but it is on the order, in this case, of hundreds of millimoles. So, and that's done to see if it will work in that case.
Hey Matt, great talk. Luke Stella from the Australian Centre for Astrobiology. I was really interested in seeing those dimers come up, and I was wondering if you saw anything longer, longer polymerization, and
Right.
if not, what you could do to maybe promote that and get some nice little polymers forming.
That is a fantastic question. By mass, so unfortunately with NMR, you're kind of looking at either monomeric phosphate or dimeric phosphate or polymeric phosphate, if you will. Dimeric and polymeric phosphate look the same. When we looked by mass spec, we only saw the dimer. So trimer would be excellent, but we didn't happen to see that far ahead. So right now, only the dimer is all I can say conclusively.
Thank you.
Mm-hmm.
I have a question.
Okay.
So thinking about the last 2 talks, so if you have ammonia that's required for this reaction, do you think it's possible that that ammonia could be generated by some of these iron hydroxides from, say, reduction of nitrate or nitrite?
Right. So, of course, there's the mixing of this chemistry involves very reduced phases, very oxidizing phases. The ammonia is a pretty reduced phase as well. So, yeah, I mean, I suppose that if you had an environment that you had pretty spatially different types of disequilibrium, maybe something like that could arise, where you had your reduced ammonium and phosphite in one area that then came in contact with peroxide and the iron as sort of the boundary. That would be an interesting possibility. Europa, maybe.
Great, thanks.
Okay, thank you.
Our last speaker is Yuda Hirakawa.
Okay. Hello, everyone. I am Yuta Hirakawa, PhD student at Tokyo University in Japan. Today, I will talk about the effects of borate on selective phosphorylation of ribose on the areas. My research interest is the origin of RNA and the origin of nucleotide. And the RNA is one of the most important molecules for the origin of life. and it can hold gene information and catalyze some chemical reactions in your body. So many researchers suppose that primordial life used RNA for their application. This theory is called RNA world hypothesis, and based on this hypothesis, the RNA formation is a crucial step for the origin of life. And RNA is a polymer of ribonucleotide, so we need to make ribonucleotide first. And ribonucleotide consists of three components: ribose, nucleobase, and phosphate. First, I'll introduce the previous research of probiotic nucleotide formation. And many previous researchers, have tried nucleotide synthesis, and left figure shows the nucleotide synthesis pathway, and right figure shows the nucleotide phosphorylation. And nucleotide synthesis generally needs step-by-step reaction using small reactive molecules like cyan molecules or cyanacetylene. On the other hand, the nucleoside phosphorylation is a one-pole reaction using small catalysts like urea. And common point of this previous research is the reaction order: nucleoside synthesis first and following phosphorylation. On the other hand, we can also assume the alternative pathway: ribose phosphorylation first and nucleobase addition later. However, the previous research focusing on this alternative pathway is limited. Some papers showed nucleotide formation from ribose 5' phosphate, but as far as we know, no one reported the ribose 5' phosphate formation from ribose and phosphate under the prebiologically plausible condition. This motivated us to investigate the ribose phosphorylation on the areas. And so why is it difficult to form ribose 5' phosphate? There are two reasons: stability and selectivity. First of all, ribose is very unstable sugars in heat condition. And phosphorylation generally needs heat and dry condition, but ribose is easily broken down and reacting each other in such condition and turn to brown tar. And second, it is difficult to phosphorylate at right position of ribose. This previous research tried the ribose phosphorylation, but ribose 1' phosphate was selectively formed, not 5' phosphate. For the chemical evolution to RNA, we need right structure molecules, so it is necessary to form ribose 5' phosphate. These two issues make it difficult to form ribose 5' phosphate. So to solve this problem, we focused on borate. Borate will have existed on the evaporative environment on the areas, and borate can stabilize ribose by forming this ribose-borate complex. So borate-rich environment could have accumulated ribose on the areas. Borate also contribute to the regioselective phosphorylation. This previous research reported the nucleoside phosphorylation at 5' hydroxy. So we consider that we can apply these borate abilities to ribose phosphorylation. So the objective of this research is to investigate the effects of borate and borate-rich environment on the phosphorylation of ribose to find a new alternative route to nucleotide. Okay, let's move on to the experimental method. For the ribose phosphorylation, we performed the thermal evaporation experiment. The experimental procedure is pretty simple. First, we prepare the aqueous solution containing ribose and disodium monophosphate, and boric acid, and the urea as a phosphorylation catalyst. The solution was heated for 24 hours at 80 degrees C with the lids open to evaporate the solution. After the experiment, we added the sulfuric acid solution to the sample and heated it for 1 hour at 90 degrees C to separate borate and urea from ribose. And then we analyze the sample by HPLC-MS. Here is the result. The upper figure is the standard of ribose phosphate, and lower figure is the experimental product. And x-axis is the retention time, and y-axis is the intensity. The black line is the standard of ribose 5' phosphate, and this is the target material. And the blue line is the ribose 2' phosphate, and yellow line the ribose 3' phosphate standard. And right figures are the fragment pattern spectra of ribose 5' phosphate and experimental product. These data show that ribose 5' phosphate was selectively formed in the reaction. And these fragment pattern spectra also indicate that this peak is ribose 5' phosphate. We calculated the yield based on the peak area, and it was 22%, and this yield is significantly high as a probiotic reaction. Here is the result in the absence of borate. We could detect the ribose 5' phosphate, and this fragment pattern spectra also indicates this peak is ribose 5' phosphate, but the yield was only 4%. So these data show that borate can improve the yield of ribose 5' phosphate. We also evaluate the product amount of each other pentosis in addition to ribose, because while ribose was selected as a sole RNA component is also a significant problem for the origin of life. Here is the result. The upper left figure is the result of ribose experiment, and upper right is the Rabinose experiment, and lower left is xylose, and lower right is Rixose. And each yields were 22% in ribose, 8% in Rabinose, 4% in xylose, and 11% in Rixose. So surprisingly, ribose experiment had the highest yield among all other pentoses in the presence of borate. On the other hand, in the absence of borate, each yields were 4% in ribose, 4% in Rabinose, 2% in xylose, and 2% in Rixose. So there was no apparent difference in the yield in the absence of borate. So these results suggest that borate can increase the selectivity of ribose. So ribose is very unstable sugars, and other sugars must have existed on the prebiotic earth. So it remains unclear why ribose was selected as sole RNA component. Some previous research reported that borate can contribute to the preferential formation of ribose. And in this research, we also found that borate can contribute to the preferential phosphorylation of ribose. In other words, borate can increase the selectivity of ribose, not only sugar formation, but also nucleotide formation. Okay, let me summarize my presentation. This figure shows the reaction pathway, reaction route to nucleotide in biosynthesis, this study, and previous research. In this study, we found that ribose 5' phosphate was formed with 22% yield. This reaction is one-pole reaction, and the yield was significantly high in the presence of borate. So we can consider that this reaction is geologically plausible. On the other hand, previous research nucleotide synthesis needs step-by-step reaction using very unstable molecules and very complicated procedure. On the earliest, the one-pole reaction must have preferentially occurred compared to the step-by-step reaction. These findings open the new route to nucleotide, and this route is phosphorylation occurred first and nucleobase combined later. This route is more geologically plausible than previous research route, and it also close to the order of biosynthesis. In conclusion, we found that borate and borate-rich environment could have contributed to the preferential formation of ribose 5' phosphate, and further chemical evolution to RNA would have occurred in the same environment. So these findings show that the borate-rich environment could have been a probable place for the origin of nucleotide and RNA. This is the summary and end of my slides. Thank you for your attention.
We have time for a couple questions.
Steve Benner, a very nice talk. Thank you very much for that. As you know, your supervisor, Yoshi Furukawa, has isolated with students ribose from meteorites.
Yes.
Is there borate in those meteorites?
Actually, we don't find borate minerals in the meteorites. So
do you have any speculation as to how ribose got into the meteor? I mean, it seemed to me that it would be very nice to have borate there because of your work.
Yeah. Yes, we try to find the reaction pathway in forming ribose in meteorites, so simulating meteorites condition. So please wait for our result.
Matt Pasek, USF. So you might have said it, but what is your phosphate source in this case?
Our phosphate source.
Sorry. Okay.
Yeah.
Cool. So sodium phosphate. Okay.
Yes.
Hey, Yuta, Luke Stella again. Big fan of your work, love everything you're doing. I was just wondering what pH you're using at those experiments, and in light of that, we had a chat before around how some borate minerals can be very insoluble at higher pHs, and I was wondering if you thought about, like what mineral source you would have for your boric acid and how that might be impacted by the pH.
I don't. In my experiment, I don't use some borate minerals, and but we assume that some tourmaline borate-rich minerals is potential borate source because the tourmaline was found in alkaline metal sediment, and so we consider that the tourmaline is the best candidate for the borate source in our experiment.
And what pH is the experiment conducted at?
The pH is around 9.
Okay.
Yes.
Cool. Thank you.
Thank you.
All right. Thank you very much.
Thank you very much.
So that concludes our session. So thank you very much for your attention, and thanks again to all our speakers.